Hi, everybody. Today is Wednesday, April 26th. We are in ES 2110 statics. And today on our schedule, the homework for chapter 5 is due, and we've already done 6, 7, 8. So we're skipping to chapter 9, and we're going to begin chapter 9. Put a smiley face after that because chapter 9 is the very end. This is the last chapter that we will cover in statics. So we are on the home stretch. Next week, we will have a meeting on Wednesday as usual. And as always, I'm available to visit at other times as well. But 2 weeks from today will be the first day of final exams. So on your Moodle page, the first thing I want you to notice is I have put up some times when you can take your final exam. And if none of these times work, you can contact me and I will work with you at a different time. Just make sure that you let me know by Friday, May 5th, so that I can keep my schedule. A couple of students in this class have also asked if they can take half of the final on one day in 1 hour and half of the final the next day in 1 hour. It's fine with me as well. Just have to let me know, because once I give you the whole test, it's over. But if you only have an hour, I'll give you 2 problems instead of 4 problems, and we'll be good to go. All right, so let's talk a little bit about chapter 9. Chapter 9, we start talking about distributed forces, and we're getting into this idea of a moment of inertia. And we're only covering sections 9.1, 9.2, and 9.5. So what we're talking about when we talk about a moment of inertia is a moment of an area, which we're not going to be talking about. There are mass moments of inertia similar to that we talked about with the centroids, the center of mass, center of gravity. When we talk about a moment of inertia, we are specifically talking about a moment of inertia of area. So let me draw you a little idea. What is a moment of inertia? Well, the most important thing to know is it is primarily a mathematical concept with many, many applications. Also, because it's quite lengthy to write moment of inertia over and over again, I'll often just abbreviate it as MOI. What a moment of inertia is, if you have some sort of a shape, okay, here's the y-axis and here's the x-axis. And if you were to attempt to rotate that shape about one axis or about some other axis that is not the x or y axis, depending on the shape and the distribution really of the mass, but in this case, if the distribution of the area, if and only if the density is constant, the density of the substance is constant, and also the thickness is constant. So in other words, we're talking about an area because basically if it has some thickness, we're talking about having the same thickness, and we're talking about it as having the same weight or mass per volume throughout. So that's how we get to the idea of working with an area. But if we're spinning things, there's a couple of things that you may see pretty quickly. One is if we had an axis here, for example, and we were spinning this object about this axis, it would take less boost than it would to spin it about this axis. The reason being, mathematically, if you think about this, if you think about the equation, force is equal to mass times acceleration, you can say then that mass resists force. Okay, and sometimes the idea of mass can be considered inertia, which basically means the tendency to sit still. Now, this is a little general. This is not highly scientific. It's a way to think about what a moment of inertia is. So this resists force, or we could say opposes linear acceleration. So if we go back to this equation, the more mass we have, the less acceleration we're going to get for the same force, or the more mass we have, a given acceleration will take us more force, right? So how does this relate to the idea of a moment of inertia? Well, in the same way, let's see if I can do it this way, that force equals mass times acceleration. And we're talking here about translational motion or straight line motion. We can also talk about rotational motion, and we can say that some sort of a moment about some point is going to equal something that opposes an angular acceleration. And that something is called I, which is the moment of inertia. Okay, so this is not a direct mathematical proof, it's just showing a concept. Okay, so you think about pushing something, takes more push to move it in a straight line if it has more mass. Take something rotationally, it's harder to spin it if it has more of a moment of inertia. So the first thing to notice is, first of all, let's talk about units. Mass, maybe in units of kilograms, acceleration, maybe in meters per second squared. That gives us force in units of kilogram meter per second squared, which is called a Newton. Okay, here, kind of work it backward. We can say a moment we know is a force, like a Newton, operating through a distance, like a meter. Angular acceleration is in radians per second squared. Radians is actually dimensionless. So if we think about it that way, we can say Newton meter second squared equals a moment of inertia. Or if we take this back to kilogram meter per second squared times meter times second squared, we can see that we get a kilogram meter squared is equal to a moment of inertia. Okay, so there's a little bit difference. They are not the same units, but there's the same tendency to think about inertia as being a resistance to some sort of motion, in this case translational, in this case rotational. Okay, so having said that, another thing about mass, everything that we've considered here, we've not considered the size or the shape of an object. So mass is just in the way, and mass is also scalar, right? So it opposes something in a purely translational way and without consequence to the shape. Now, with a moment, we can also see that a moment has to be taken about a particular point or an axis. So therefore, we have to think about what a moment of inertia is about some axis. So in other words, it's not just a point feature of an object, but it has some relationship to the shape of the object. Okay, so for example, here we have this rectangle, and if we wanted to spin this rectangle about an axis that was right in the middle, in other words, a centroidal moment of inertia, it's going to spin much easier. You can think about it, if you flick it, if it was on a fixed axis and you flicked it, it would spin pretty nicely and pretty evenly. If, on the other hand, we wanted to spin it on its edge, it would take more of a push to get it going. And then in the absence of anything else, it's going to be somewhat lumpier, is the expression I would use. Once again, not a technical term, but there you go. If you have, and in some of my classrooms, I have something that I can use to demonstrate this. Everything here is disappointingly symmetrical, so I'll draw a picture. But if you have something that lacks symmetry, like if you have, let's just say I'm trying to think of what those are called. They're called like, well, they're called like rolling rulers or something. Let's just say you had something that looked like this. Okay. If you had a ruler that had a straight edge on it or something like this, if you spun this about an edge, it's going to be quite lumpy, high moment of inertia. If you spun it against something over here, it would be less lumpy, lower moment of inertia. And if you were able to identify the location of the centroid and spin it about the centroidal axis, that's where it's going to be the most balanced. Okay. In other words, take the least amount of a moment in order to get the same acceleration, angular acceleration, or to get more angular acceleration for a higher moment. So that's kind of the way it is. So the moment of inertia is different for each axis. All right. Now, here's a place where the math from chapter 5 will help us with the math from chapter 9, because it looks very much the same. As I said, primarily a moment of inertia is a mathematical concept, and it turns out that I, about an x directional axis like this, is going to equal the integral of y squared dA. Much like you might remember q sub y is equal to the integral, I should say q sub, let's do q sub x, sorry. Otherwise it's unnecessarily confusing, is equal to y dA. So in other words, we call this q sub x the first moment. And this, if you think about it, because y times something, a distance times something is a moment, this is the moment of the first moment. And for that reason, we also can call it the moment of inertia. I've heard it called the second moment of area or the moment of the moment, but moment of inertia is the standardized term for that mathematical concept.
So our first moment, yeah, is the mass or area.
Area.
Mass of kilograms, y is the distance by meters.
Yes.
So that first moment is a kilogram unit or.
Well, okay,
Isn't it? I shouldn't say
based on mass
unit.
is equal to this.
That's our.
Okay, right.
Yeah.
And so similarly, if we were doing this based on mass, the integral of y squared dm. Okay, but let's go back through this because this is a really good question. Mass, we know, is density times volume, right? So if density is constant, if we're looking at a dm term, the integral of a dm term, we can say it's the integral of rho dv, which is equal to rho times the integral of dv, right? Further, if thickness is constant, we can say that the volume of a three-dimensional object like this, if we call that dimension that we're not examining the thickness, and we call this the area, we know that volume is equal to area times thickness, and thickness is constant. So therefore rho times T dA. See, so what ends up happening is rho times T comes outside the integral and divides itself out in the long run. Yeah, so it's a little squiffy. My math is not going to hold up for an analytical math, but it works. This is why we're extrapolating to this. Now, this also brings up the point, like we're talking about units here. Okay, in the same way that a center of mass is going to have units here of dm or mass and y. So we're going to have some sort of a moment unit, right? We're going to have a moment of a moment here, but in terms of area, it's going to be length to the fourth power when we finish off, instead of being basically a length squared times a mass, right? as it would be up here if we were really using units of mass, if we weren't building in this assumption that rho and t are constant so that we can base everything on area. This would be a length times mass. Here it's just going to be a length to the fourth. So when we do this, come up with length to the fourth. All right. So let's take a look at how one solves the problems. The first thing is, for a shape like this, we have a rectangle with a semicircle cut out of it, right? So we can think of it as a rectangle minus a semicircle to get this composite shape. So in other words, in sections 9.1 and 9.2, we can start looking at that composite shape stuff, just like we did in when we were talking about first moments or q sub x's and q sub y's. I want to take a look. Yeah, I was going to say that's 9.3. I just want to make sure I wasn't. I want to make sure I was going far enough with my discussion. So, I pulled some pages out of my book. Well, isn't that interesting? All right. So next time I'll bring the other book. I was looking at stuff and I thought I'm missing a couple pages, and I know where they are. So here we go. So we've got this sort of a thing. Now, here's the idea. Just like there is in first moments, we had charts that showed us the first moments of inertia for different common shapes. There are the same chart has the moments of inertia for those same common shapes. They're all based on that equation of what we have there. Well, I have just destroyed my book. It is time for the semester to be over because I don't even have it here. So let me see if I can find it. If you look, for example, here, it states I sub x is equal to 1/3 BH to the third. Your book has that chart. Oh, now you're looking at the rolled. Okay, no, you're on the right page. I thought that this is the rolled shapes. Here you go. Yeah, so this is, yeah, so let me just, I'm worried for a second. I'm just gonna put it up here on the screen since I've lost my phone. I'll give it right back to you. But here we go. So here's the chart in the textbook. What I want to point out to you is when you look at the moments of inertia, we have I sub x and I sub y moments of inertia. We also have something called J sub c, which is called the polar moment of inertia. It is J sub c, arithmetically, is I sub x plus I sub y. Okay, now I sub x bar, this is actually redundant, but when it says I sub x bar, that technically means it's about the centroidal axis in the x direction. So you'll notice that I sub x, for example, here's my x-axis. So here, I sub x, they're talking about the centroidal moment of inertia taken about this axis. I sub x, they're talking about it being here. Okay, same thing here. I sub y bar is here. I sub y is here.
It's y-axis.
That's correct.
About y-axis.
That is correct. Right. So you always have to look at the picture to see what axis they're talking about. But it is common that when it has a bar above it, they're talking about the centroidal moment of inertia. So about the centroid, wherever that centroid is. And you'll see here, for example, here we have I sub x and we have I sub y for the semicircle. Neither one of them is called out as being centroidal, but you can see that this is in fact centroidal because y goes through the centroid. So in other words, you just have to equate this equation to this picture to get the right axes. The other part is J sub 0 or J sub c also tells you what it's about. So for example, J sub c, so each I sub x, I sub y are about axes. J, or the polar moment, is about a point. J sub c means it's about the point C. Okay, J sub O means it's about the point O. J sub O means it's about the point O. J sub O means it's about the point O. J sub O means it's about the point O. So you just have to kind of equate those things with each other. Okay, but the one thing that is fairly consistent when there's a bar above the moment of inertia, it means about the centroid in that direction. Okay. So the first part of the work, we're going to just work with centroidal moments of inertia, or not centroidal, but excuse me, but moments of inertia that can be found by composite shapes. Now, as long as you reference everything about the same axis, like when I have a composite shape like this, where I have a rectangle minus a semicircle, as long as I'm taking them about the same axis, whatever that is, I might have to move it, which I'll talk about later. But as long as I'm taking it about the same axis, I can just arithmetically add them together. If they're not about the same axis, I have to move stuff, which we can talk about later on.
I'm noticing.
Uh-huh.
It's about
Yes,
have a moment on the x-axis about 100.
yes,
And then have about the x-axis.
yes,
It's 1/4.
yes.
I'm assuming if we're dividing that level by 2.
Uh.
once. For the first moment, we divide it by 2 again, that comes out to be 1/4, and that's why it's a quarter of that.
In this case, yes.
Trying to think through them, right, in that
Right.
particular case.
No, I think that in that particular case, in section 9.2 or 9 point, the next, whatever the last one is that we're going to study, there is a theorem called the parallel axis theorem, which basically says that in order to move the centroidal axis to some other random axis, so I sub x bar, if I want, oops, that's not going to work. There we go. If I want to translate it to some other I sub x, I add to this the area of the shape times the distance squared, where the distance is the distance from the centroidal axis to the other axis. So, right,
Which makes that.
it does, doesn't it? So, the only thing to remember, and I don't know why this is something.
That's why they're.
Yes, that's exactly right. Right, because if you look at that integral y squared dA, if y was constant. Which is right there. Yep. So anyway, in the same direction, there's 2 points that are important to note. One is this has to be the centroidal moment of inertia, the centroidal I. Because in other words, you cannot move this between 2 random axes. You could only move it between the centroidal axis and 1 random axis. See? Okay. The other point is because this is squared, the centroidal moment of inertia is always the smallest moment of inertia for any given shape. Any shape, always. That is correct.
So this would be useful, but I'm thinking, why would you just do it?
Yes,
Instead of doing it twice in the meeting.
right.
But if you have an object like a rectangle, it's easy to take geometrically,
Yes,
then you can just move it without. Okay.
perfect. That's exactly correct. And so, yeah, so it can be very, it's a very powerful tool. It's a big old hammer in the toolbox. Okay, so here, this will be the first part of the homework, using a composite shape, where we find the moment of inertia of the rectangle. You see it's I sub x, not I sub x bar. That means that we're taking it about this axis, right? And it says it's 1/3 base height to the third, which is agrees with the chart. And we find this value. Then we have to find the moment of inertia of the half circle, which we find the area, we find the distance between the centroidal axis of the half circle and the axis that we're taking the moment about, right? Because in order to arithmetically add or subtract them, they have to be about the same axis. So, and we have to start with the centroidal moment of inertia of this, and then move it using AD squared. And then, so there's here it is right here. They call it AA squared, which I think is kind of ugly, but there you go. So then you find not the centroidal moment of inertia of the half circle, but the moment of inertia of this half circle about this x-axis. Okay, then once you find that, you can add those two together, which involves, because this is a negative area, subtracting the second one, and you get I sub x of the composite shape. So in other words, this value, 45.9 times 10 to the 6 millimeters to the 4th power, is the moment of inertia of this composite shape about this axis. Okay. So it's actually a little bit easier because than doing Q sub x and Q sub y, because you don't have to do the weighted average to find the moment of inertia. So, you know, how to find the centroid. Sometimes you might have to do this to find you might have to do the first part that we did in chapter 5 to find the centroid of an object. And then to find the moment of inertia, because once again, you can't move between two random axes. You have to move between a centroidal axis and a non-centroidal axis. So, what do you think? Right, and we're not, that'll come up in dynamics. Yeah, we don't even have to work with this, but basically, this is Newton's second law. Exactly, for rotation. Yeah. No, angular acceleration. Yep, good question though. But they're all directly related. It's
That's a
oh,
velocity.
right. This is rotational velocity. Yep. Ah, very good. Yes. L is usually linear momentum. And L dot would be the rate of linear momentum. And then H is angular momentum. Those are fairly standardized. And you get to work with that next semester in dynamics. Won't that be fun? Yes. Dynamics is fun. Conceptually, once things start to rotate, we have to open up another part of our brains.
We use the work and energy laws to figure out the roll of block
Yes,
that's solid down a slope.
yes,
You can figure out how fast it's moving translationally
yes,
by removing the energy that goes to rotation.
absolutely.
And then you compare that directly to one that's just a shell, a hollow. So
Very nice.
using,
Isn't that great?
but we did it using letters.
Right.
So it's finite. We can just plug and chug.
No, but that's great. It's great that you like that. Some people sort of balk at that. So, yep. So, yeah, so that's it for today. We can get started on the chapter 9 homework. And I don't think this is a very long problem set, but it's deceptively, I shouldn't say deceptively. There aren't that many problems, but every problem will take some time, right? So we have 2 problem sets. The first one is 4 problems. The second one is 3 problems. So it's just a total of 7 problems for the entire chapter. And then when you're done with that, you're done with all the homework for statics.
I have a question.
Of course.
5
Yes.
and 5.53.
5.53. Let's see what we got.
I'm curious what yours looks like in your book. Mine looks very different than this now. My universities are telling me it should. So it is difficult to know if I'm doing it right or wrong.
Problem 5.53. Oh, and you are, yeah.
I'm in the 11th edition.
Okay, I might have that. Hang on. I'm going to do something here. I'm going to go ahead and turn this off. All right, that's it for today, gentlemen and ladies. Thank you very much. But I might